This is your last lesson in our unit on statistics, and this lesson is on a concept called residuals, which is a little bit related to your correlation coefficients, or the R values that we found in the previous lesson. So in the last lesson, we saw how the correlation coefficient, or R value, measures the predictability of the model. In other words, if I use it to predict a value that I don't actually have, is it going to get pretty close to the real value, or is it going to be way off? Although the R value is an excellent measure, it does not tell us whether the model is appropriate. In other words, whether a linear model was a good choice, or if we should have chosen exponential or another option. It only tells us whether it does a good job at predicting other values. So today we will examine what are known as residuals and residual graphs to determine if a linear model makes sense. Again, we're focusing on a linear model and thinking yes or no, but keeping in mind that there are other models out there to use that might be more appropriate, and that's what we're trying to determine. So for example, exercise 1, a skydiver jumps from an airplane and an attached microcomputer records the time and speed of the diver for the first 12 seconds of the diver's free fall. So we've got the data shown in the table below. So time in seconds from 0 to 12 and speed from 0 to 74. Part A says, find the equation for the line of best fit for this data set. Round both coefficients to the nearest tenth. As well, determine the correlation coefficient and round it to the nearest hundredth. Based on the correlation coefficient, characterize the fit as positive or negative and how strong of a fit it is. Create a plot with both the data and line of best fit shown on it. You do not need to reproduce the plot below. So if you need to take a moment to open up Desmos and put in this data from your table and then put in your approximation for the line of best fit, go ahead and pause your video now, read through the instructions carefully because it asks you to do several different things in a row. And then once you've got yourself set up and you've got your equation for your line of best fit and your correlation coefficient, come back and take a look at, we'll work through it, talk through it together. So here's what my graph looks like. You can see the points in green and the line of best fit in black. Hopefully you've already copied down your parameters for M and B, your equation, and your R value on your sheet. If you haven't done that, go ahead and do that. So an R value of 0.94 shows it is a strong, positive correlation. But just by looking at the graph, actually, we can see that a linear fit is probably not our best option. So although my line of best fit is a decent predictor of the values that I don't have, especially I'd say between the first and last values that I have, a quadratic fit would probably be more appropriate. So how would we know that? Just from looking at our equations. Our R value, our correlation coefficient, actually says this should be a pretty good predictor. So how are we supposed to know that there's another model that would be more appropriate? The part B says the residuals of a data point is defined as the difference between the observed Y value and the predicted Y value. Use tables on your calculator, fill in the table below with the predicted values, round to the nearest integer, and the residuals for each data point. So the first thing we're going to do is figure out what our model, which is this 6x plus 13.1, would predict for each of these times. So again, with Desmos, the easiest way to do that is actually to give yourself a new equation, type in y equals 6.0x plus 13.1. There's my equation. I'm just going to change the color. I think orange. So there's my equation. You can kind of see it differs a little bit from the black line, which is the predicted line, just because I rounded. So there it is on there, and then I'm going to convert it to a table, make this into a table so that I can get the values for these particular x values. So I need my x values for 0, 2, 4, 6, all the way up to 12. So I'm going to start typing them in down here. I can just type it in straight. So 0, 2, 4, 6, 8. Oops, there we go. 10, 12. So these are all my predicted values for my orange line, which is my line of best fit. This is what it would predict for each of my data values. So if I go back to my table, I'm going to copy those in, and it says round to the nearest integer. So I'm going to ignore these 0.1s that I've got going on here. So maybe pause your video for a minute to do that yourself, to put in the equation, converted it to a table, make sure that you know how to do it, and then pause your video to copy down this data onto your worksheet. So once you've copied this data into your table, we can now use our table to find the residuals. So the residuals for each data point is the difference between my actual speed and my predicted speed. The difference between your observed y value and your predicted y value. So I'm just basically going to subtract. So the first one's going to be 0 minus 13 gives me negative 13. The next one is 25 minus 25. It's just going to give me straight up 0. The next one, 46 minus 37. I think that's going to end up with 9. So we're subtracting. 60 minus 49. It's going to give me 11. 68 minus 61 is 7. 72 minus 73 is going to be a negative 1. And the last one, 74 minus 85, I believe is going to be a negative 11. So that's how we find my residuals. 74 minus 85, take your actual speed and subtract the predicted speed. These are going to be my residuals. So that was part B. Part C says, sketch a plot of the residuals below. Your teacher will show you how to do this on your graphing calculator. Make sure all other scatter plots and equations are off. Do the residuals show any distinct pattern? So you could take these values, these residual values, and put them back into Desmos in our table, and we can actually just add a new column to the table if you wanted to. So this could be, say, y2, and then put in all your values. So the first one was negative 11, and keep going across, and they would start showing up. Or you can actually just click. This is the easier way to do it, but this is useful if you need to add values to a table. Anyway, if you just click here where it says residuals and plot, boom, whoops, mine moved over too far. This is what should show up in your table. Delete that. There we go. So I've got, there's my negative 13. This one was 0 on mine because I'd rounded, but you've got, again, can see these all plotted on your graph. And you may need to change the window a bit in order to be able to still see everything if it's down below where you had your window before. So here are all my residuals, those subtracted values that I got in my table. So again, to do that, there was just a little button here that said plot under residuals, and if you click that, it will automatically put it into the table that you had up there before, so you can see what those residuals look like. Now if I go back to my question, it says sketch a plot of the residuals below. Your teacher will show you how to do this with your graphing calculator. Make sure all other scatter plots and equations are off. No worries about that. Do the residuals show any distinct pattern? So if I'm looking at it, does this look like they are going in a predictable pattern? And in fact, they do. They also look like a quadratic. So this is my clue, actually, that my linear model is not a good choice. If my linear model had been a good choice for a predictor, an appropriate choice for a predictor, then these points should be all over the place. I should have some too high, some too low, but they should be, I mean, they can be scattered all over, but they shouldn't be showing me something so nice. It looks like such a nice pattern. So that is the clue that I've got, that a linear model is not the best predictor. So do they show a pattern? Yes, there is a pattern. They appear to form a quadratic function. Now I don't know that that necessarily means a quadratic function is what you should have used as your predictor, although in this case it is, but they do show a pattern. And that is a clue that a linear regression is not the most appropriate best fit. Quadratic best fit would have been much better, and actually we can see that just down below. If I add a new expression, oh, this is a little bit annoying. It's off the bottom of my screen. Where is it? Okay, there we go. So now you can see on there that a quadratic function would be a much better approximation of my data points. And here again, for the quadratic function, I can plot my residuals if I wanted to. Let me just take off these residuals so that you can see they're much more close to 0 and they don't show as much of a pattern. Now there's a little bit of a pattern here. They kind of go up and come back down again, but it's pretty close. It could be a straight line. So generally, we do not want residuals to fall along a curve or make a distinct pattern. If so, then it's likely that a linear model is not appropriate to fit the data. Perhaps an exponential or quadratic model or another function is better. So there's our hint. So let's take a look at another example. A school district was attempting to correlate the number of hours a student studies in a given week with their GPA. They surveyed 8 students and found the following data. So again, we've got a table with hours and GPA, and we're asked to do all those things we did for the first question. So it says find the equation for the line of best fit and the associated R value, round the linear coefficients to the nearest tenth and the R value to the nearest hundredth, then create a scatter plot with both the data and the line graphed. You do not need to reproduce that graph here unless your teacher asks you to. So again, pause your video, go ahead and put this information into Desmos and find what you're looking for, then come back. So here I've got my scatter plot with the line of best fit graphed there for you. So again, you might need to adjust your window to make sure that you can get everything on there, and you can do that here with this graph settings wrench. And so I can see here my M is 1.3, my B is 73.7, and my R is 8 or 0.88. It's going to round to. So make sure you copy all those down, and then we're going to move on to part B. So part B asks, what is the value of the residual associated with the data point 1194? So in my original table, I have the data point 1194, and I want to find the residual that's associated with this data point. So before we found it for the entire row for the whole table, and now I'm just going to do it for just one data point. So in order to do that, the first thing I need to find, if you remember, is the predicted value for 11 hours of studying. So I'm going to find that by plugging into my equation. So then my y equals 1.3 times 11 plus 94. Plug that into your calculator. And I figure that is 108.3. So that is my predicted GPA based on the model. Sorry, I just realized that I added 94 instead of 73.7. Let me go back and fix that. So plus 73.7. And that gives a more realistic GPA of 88%. So there's my GPA of 88. To find, that's my predicted value for my GPA. Whoops. Give that 1. And now to find my residual, I'm going to take the actual value. So residual is actual minus predicted. So that's going to be the actual of 94 minus the predicted value of 88 would be 6. So my residual in this case would be 6. Part C says, produce using your calculator the residual graph. It does not need to be exact, but show your window and the correct general location of the residuals. So we're going to go back to Desmos, and we want to plot. So again, before this disappears, you want to hit this plot button, and it's going to show your residuals on your graph. Now, nothing showed up because, again, my window is not including these values. So I'm going to need to either zoom it back out again or just use my wrench to take it down, I need to go to at least -5, it looks like. So on my y-axis, I gotta go a whole lot lower so that I can see, there we go, I can see my residuals now on the x-axis. So sketch a quick general idea of where these line up on your graph in this space that's right here. Draw yourself a quick XY axis, and then in general where the points are. You don't have to be super exact, but copy this onto this little space right here. Pause your video if you need time to do that. And then the last question, why does this residual plot show a more appropriate linear model than the one in exercise 1, even though the R value is worse? In other words, why was a linear model a good choice for this graph more than it was for our first graph? And because we're not seeing any pattern in the residual, they're just kind of scattered around 0, that's what's telling us that a linear best fit was actually the best option. So we're going to say the residuals for this model indicate a more appropriate linear model because they are randomly scattered. There's no pattern across the x-axis. So the predictive power of the model is not as good because the R value is not as good, but it's still a more appropriate model because of your random residuals. All right, that's it for this lesson. Hopefully that wasn't too much to handle, and we'll see you next class.